Make a start. I'm going to talk to you a little bit about the way that we're going to mark assignments and stuff in the project session at the end, because I don't want to waste too much time today. But the basis of it is you're going to get a percentage mark instead of a grade now. But I'll explain that more later. So, what you're really here for in this session: computational and analytical methods. So what we do in this module is build on some of the mathematical modeling techniques you studied in your first year mathematics, and also go a little bit that you probably had to go with autograph with Mark, but we're going to do a little bit more around that area and have a look at an analysis that you would do with SolidWorks as well as part of the portfolio or assignment. So for learning outcomes, number one, apply further integration techniques and use numerical methods to evaluate functions. So we're going to do some more advanced differentiation and integration techniques. Form and solve first order ODEs, that's ordinary differential equations, and second order ODEs as well. Evaluate the use of 2D and or 3D software methods to generate models and solutions for engineering components, and investigate the use of 3D CAD modeling techniques to evaluate models for design performance. So there's two assessments. First of all, there's an examination largely covering learning outcomes 1 and 2, and that is of 2 hours duration, and that will take place in May, in the 3 weeks after the end of the 12-week second semester teaching period. Now, so this module goes all the way through the year. Yeah. The only exam you've got in January is the mechanical principles exam. No. We have kind of agreed the dates with the course team, but the documents detailing them are back with the team members for checking to make sure they're all right, and then I'm hoping to have them with you either next week or the week after. You'll have your exam dates, all right? And that includes the May one and the Christmas one, all right? And then the second part of the assessment is the portfolio of roughly 2,000 words covering learning outcomes 3 and 4. You'll have a look at a couple of 2 or 3, I think, significant mathematical models of some data and some work with SolidWorks for that portfolio. And I got the hand into that around Christmas time, just after Christmas. Okay? So that's what we're going to do over the coming weeks. Each of those 2 assessment methods is worth 50% each. So there's no kind of waiting with that. You've got to obviously pass both parts of it, but there isn't no waiting towards the exam or towards the assignment. A little bit, but when we're going to do part of the models that we're going to do in 3 and 4. Are naturally going to include some techniques, because what we're going to do is do the manual way of calculating, and then compare that with the software and how the software goes about achieving that a little bit. Okay, particularly with the autograph software and some of the techniques. So yeah, although us tried to define in those 2 and those 2, there is a little bit of crossover between them. It's really helpful. So, in good old Mr. Jackson parlance, let's start off with a little bit of a drill, should we? I've got a handout of today's slides for you. So if you want to take one and pass the rest round. First of all, the graph on the first slide is a partial plot of the function shown there, 3x cubed 0.2x squared minus 5x plus 6. First question, what's the term used for the points A and B on the graph as shown? Second question, what's the value of the slope of the graph at points A and point B? Indicate on the graph a point where the slope is positive and another where the slope is negative. How do we represent the slope of a graph in mathematical notation? For the clever of you, there are two different ways we might notate that. And indicate the point that represents a root of that function. And on the second page, what's the value of x to the 1? What's the value of root 9? Have a go at answering those questions as well, as a little preamble to what we're going to do today. About 5 minutes on that, okay? Right, what do we reckon then? Terms for the 2 points, A and B. Anyone got any ideas? Anyone offer anything up? Ed? Turning points would be one term you could use, yeah. Can you specifically, though, separate A from B? Yeah, I'll put it up here. A, a maximum, B, a minimum. The other thing, though, to consider is if we say we're looking here between x as minus 2 and plus 2, you'd probably qualify that a bit more and say they're local maximum and minimum, because in a more complex function might be possible to have further maximum and minimum points if you're looking in a different area. Okay? But actually to say within the area you're looking at, that's a maximum and a minimum, that's fine. Okay? And part of the work that you can do with differential calculus is find these maximum and minimum points of interest. Okay? So, second question, what's the value of the slope at those 2 points? Did you say that, David, or did Curtis? It's 0. Yeah, when we talk about the slope on a curve, we're talking about what's the tangent to the curve at that point, and a tangent to those curves at those 2 points would be a straight horizontal line left to right, and therefore the slope of that is 0 in both cases. So where might we indicate on the graph a point roughly where we would see a positive slope and another one where there's a negative slope? Leading up to A as a positive one, I'll do that in red. So we could, anywhere up in that area there, we could get a positive slope. Equally, we could have a positive slope in that area going up there. Yep. Negative leading down between A and B. Yep. So as soon as we turn around that point and start coming down here, our value of y is getting smaller as x increases, so the slope is negative. So I'll just write down there, red line, positive, blue, negative for reference. Yeah. How do we represent the slope of a graph mathematically? What do we write in terms of the calculus way of writing the representation of the slope of a graph? If we're using this function where we've got an independent variable x and a dependent variable y, how would we write that in terms of the slope? Yeah, with dy by dx, yeah. 4. dy by dx is one way to write it. If we write this as f of x is equal to that function, we might use this notation, f dash x, the first differential of that function. And sometimes that just tidy up our notation a little bit to use that method. And later on, we're going to be looking at a technique where we're going to be looking at the third, fourth, fifth, sixth, perhaps differentials. And that's a lot easier to use that notation than it is to use this one. And lastly, where's a point on that graph as shown that represents a root of the function? Where across the x-axis, yeah. So the root is there. Notice in my question I say a root, because it is quite possible, if this is a complex function and you're going to come across some that are multiple sine waves added together in electrical, where it could quite possibly cross that line again up here somewhere at higher values of x, or down there at lower negative values of x. So it is a root. It is one root, and it's the one in the area of interest. Okay? Moving on to the second page. What is the value of x to the power of 1? X. So what we're saying there is any number, x to the power of 1, is equal to that number. What about x to the power of 0? That's equal to 1, yeah. Any number to the power of 0 is equal to 1. What's the value of the square root of 9? Three. Think you need to qualify that any further? Plus or minus 3. Yeah. What about the cubed root of 27? That's 3. It's not plus or minus 3, is it? Because if that was, because that's what is the number multiplied by itself twice that makes 27. So if you had a negative 3, you'd multiply it by minus 3 to end up with a positive, and then multiply it by minus 3 again, you'd end up with negative. So it's not plus and minus for odd values of root. Okay? What about this one in non-fraction form? So we get rid of the fraction. 3x to the minus 3. Yeah, the x to the 3 comes up on top and becomes a negative. How do we write the square root of x in indices form? X to the power of a half. And how do we write the cubed root of x squared in indices form? Remember the reason, well, you may not remember, but the reason for needing to do this is if we're going to integrate these functions, a function with these in, we need to put them in indices form to do that. Anyone, any ideas? It's x to the power of, if we look at that one, the 2, the square, comes as the denominator. So the number of the root is always the denominator, so it must be x2, the 3 underneath, and 2 on top, 2/3. Okay, it's just a little warm-up covering some of the things that we need to do the differentiation, because today is kind of a recap on things that you've probably already done in your first year maths. So, on the next page, there's a table of standard derivatives. Do you remember seeing that when you've done your maths, when you've done your calculus with Mark in year 1? Okay, because we're not really interested in this module for sure. Maybe even Mark wasn't in the first module, I don't know, in differentiation from first principles. What we're going to be doing is using a table of standard derivatives to find the derivative of a particular function of a particular type. So we've got enough on there for any of the functions we're going to cover at this stage. So if we want to find the derivative of a function that is a constant times x to a power, we'd use that entry in that table to find out what the first derivative is. And notice I use both notations. So we've got powers covered, we've got exponential functions covered, we've got log functions covered, and we've got sine and cosine functions covered. If there comes a point when we need any more, then we'll add those to the table, and you will get a table of standard derivatives and integrals in the exam. Okay. So, on that basis, how do we find the differential or coefficient of y equals 12 x to the 3? What we got to do? Bring the 3 down. So we're going to write 3. We've got to keep our 12, haven't we? X. 12x. And then this index becomes 3 minus 1. Yeah. Until you get used to this again, I would recommend you writing out the stages, and then, so we got to do 3 12s are 36, x to the power of 3 minus 1 is 2. What about y is equal to 12 over x cubed? Twelve x to the minus 3. So we've moved this from the bottom to the top. We've got rid of the fractional content of that function. Okay. If you can't remember how and why that happens, I think that's in chapter 5 of the Bird book section on algebra and laws of indices. Okay. And then, so then what we do is we bring the minus 3 down, multiply that by the 12, x to the minus 3 minus 1. And then again, multiply out, minus 36, x to the power of minus 4. And if we want to, we could put it back into the form it was in originally, which would be 36 over x to the positive 4. Take it back down and make it a fraction again, if that was necessary. Sorry? Yeah. If I've got to change sign when it goes that way, must also change. Oh yeah, sorry, minus 36, yes. Spotted my deliberate mistake. Okay, all reasonably happy with that? Please shout if you are not. But there's a process to go through there, and that is the constant comes down, take one off the index, and we've differentiated that function. Okay, and there may be a need for a bit of rearranging to get it in a straight indices form. Okay, A. Y equals 6. What's the differential of y equals 6? It is 0, but can you work out what happens? What could we put in there so we bring in the variable x? We could put x in there. What power would we need to give it so that it was still y is equal to 6? Is that right? Have we still got the same thing? We still got the same thing, yeah. Because what would happen then is that 0 would come down. You'd have 0 x to the power of minus 1, and 0 times anything is 0. So what that one is saying is constants disappear when differentiating. They disappear. And B, y equals 6x. What's the unwritten index here? We don't ever write it, but what is it? Yeah, 1, we've still got the same thing. So our constant comes down, 1 times 6 x to the 1 minus 1. Equals 6. Because that becomes x to the o, which is equal to 1, and therefore we lose the variable there. Okay, so linear functions, 6 times x, that would give us a straight line graph, y is equal to 6 times x. We lose the variable and we get a constant. Okay, if you think about that, if we graph anything linear, it's a straight line, the slope of that graph is constant. Wherever we measured, changing y, changing x, anywhere on that line, we get the same value, so it must be a constant. Right? Everybody still happy with that so far? Problem 4. Differentiate 5x to the 4 plus 4x plus 1 over 2x squared plus 1 over root x minus 3 with respect to x. What have we got to do with that first? So let's rearrange it then. Do we need to do anything with 5x to the 4? No, leave that as it is. Do we need to do anything with 4x? Do we need to do anything with 1 minus 1 over 2x to the 2. What are we going to do with that? Still got to be a minus. Sure. You think that's 2x to the minus 2? Right, take that function to one side, 1 over x 2x squared, or 2x to the minus 2. Forget about the negative sign in front of it for a minute. Set x to a number, whatever number you like, and do that, and set x to 3, and do that and that in your calculator. Do you get the same thing? If x equals 3. If you do, I'll agree with you. Because that's wrong. 1 over 2x squared is not the same as 2 times x to the minus 2. Where do you think you might have gone wrong? Half x to the minus 2. Two ways of writing that, but we'll write it how you've just said it. Half x to the minus 2. Do that in your calculator. Forget the negative sign. Do half x to the minus 2 in your calculator and see if you get 1 over 18. Or if you get the same result as if you do that. That is to take, you're effectively, what you did was kind of take the reciprocal of that and change the sign to negative, but you actually only want to move, you're only going to move the x by changing the sign of the index. Okay? So just be careful, because that's a common mistake. And then, what about the root x? What have we got right there? What we got to write for root x? Yeah, because it's 1 over root x, so we'll do plus x to the minus a half, and the minus 3 will, what happened to constants? But we're only rearranging it at the moment. Okay, so we do that. Yeah? Now we can differentiate. dy by dx is equal to differential of 5x yeah, the x disappears, plus, oh hang on, that's 5x to the 4. Missed that off there, didn't I? So we're wrong. Differential of 5x to the 4. We got to do, Curtis? Yeah, so 20 x to the 3 What about the 4x? Becomes 4. We've got minus 2 as a constant here. Minus 2 is an index. So let's just write that one out on its own for a minute. We've got minus a half x to the minus 2. Yeah? And this is why I'm putting brackets around. We've got to do minus 2, bring the index down, times minus a half x to the minus 3. That'll be the new index. Minus 2 times minus a half is plus 1, isn't it? Yeah? So that's what we need to put in there, is plus x to the minus 3. Now we deal with x to the minus a half. Let's bring it on its own. X to the power minus a half. We're going to bring the minus a half down in front. X to the minus a half, take away 1. How do we write that? How many halves in a whole one? It's 2. So when we go to the minus 3 over 2. Yep. So we can write that in our big function. Minus half x to the minus 3 over 2. And then the last bit is, what do we do with the minus 3? It's a constant, so it disappears. Yeah? Is there any way we can make that a little bit tidier back to what it was in the first place? We can't do anything with the 20x cubed. We've got our plus 4. What we'll do with the x cubed, Josh? 1 over x cubed minus any ideas?
Minus 1 over
we definitely want that, won't we? Remember what we said, where does the value of the root go? The square or the third? It goes to the denominator. So it's the square root of x cubed, and there's 2 lots of it, because that's half times it, isn't it? Yeah? So that is that function differentiated. So where we've got a sum, or we've got plus or minus involved with values in a function, then we just deal with each one in turn, differentiating using the standard differential for a power function, rearranging where necessary. Okay? Everyone happy with that? I'll move on to the next bit, yeah? So, find the differential coefficients of y equals 3 sine 4x, and f of t is 2 cos 3t with respect to the mentioned variable. So it doesn't have to be x and y. We've got one here where the independent variable is t, usually for time. So have a go at those two. Go back to your standard table of differential derivatives, find the derivatives for the sine and cosine functions, and have a go at those two. Right then, I. y is equal to 3 sine 4x. What do we do with that to find dy by dx? Bring the 4 down. That stays at 3. Four remains, and x remains. And multiply that out. 3 4s are 12. Cos 4x. Yep. Okay. Rest assured, you ain't going to get anything as easy as this in your exam. And second one, f with respect to t is 2 cos 3t. What do we do that one? Jordan? Yes, we bring the 3 down. 2 stays the same. Minus sine, isn't it? Yeah. Deliberate mistake again. 3t. And that therefore it is minus 6 sine of 3t. Yep. So now we can do power functions and sine and cosine functions. We can differentiate, and I'm pretty sure if I asked you to, you could mix the two now. Yep. Over the page, there are some examples of two examples of exponential functions and an example of a log function. 3 or 4 minutes, have a go at them 3. Alright guys, how do we do this one? Y equals 3e to the 5x. Five what? 5 comes down, does it? Keep the 3. E to the 5x. Yeah. The power doesn't change with the exponential function. The differential of e to the x is e to the x. That's why it's a special function. That's why e is a special constant number, because of that. So it equals 3 5s is 15 e to the 5x. Yep. B. How do we do that one? As yep, and then do it from there. So just 3 minus 3, yeah, multiplied by 2 e to the minus 3. That is minus 6 e to the minus 3. Yeah. Yep, all happy? C y equals 6 ln x. 2x, sorry, yeah. Well spotted. How do we do that one? What does it say in the table of differentials for log function? Ln x if we've got ln x, dy by dx equals 1 over x. Yep. So the number we've got here is 2 times x as a number. That entry in that table is saying that the log of a constant times x is equal to 1 over x. So that constant disappears. So the answer is correct. 6 over x. Okay? Alright, with that, everybody happy with what we've done so far? Okay, so all the basic functions that I want to revisit, sine, cosine, power functions or polynomials, and log and exponential functions, we've just revisited them, had a little look at how we differentiate each of them, and we do that using that standard table. If you've got a folder, my recommendation would be to get a copy of that somehow, write it out and slap it in the front cover so you always got it somewhere to hand. Yeah? That would be something I would certainly do if I was doing this module, and then next week or the week after when we do integration, standard integrals, slap that underneath it. So that's always there, you can find it quickly when you're revising. Okay? Leave a little space in case you want to add some extra functions later on, maybe. Okay? Right, going on, hopefully you touched on these with Mr. Jackson in your first maths, but we need to be able to use some rules when we have functions that are multiplied by each other. So a function u times another function v, where both of them are functions of x. A quotient rule, where a function u is divided by another function v. And lastly, where we have two functions and one function is a function of another. So that would be like something like x squared in brackets, and then the whole x plus 1 squared in brackets, for instance, and then the whole thing raised to the power of 6, the whole bracketed term, would be an example of a function of a function. Or we might have a sine with an x squared function inside it, function of a function. Yeah. So we're going to have a look at some examples of using those different rules now. Whether we get all of this, all three done today, I don't know, but we'll try, and if not, we'll carry on from where we finish next week. Next week, my main plan was to have a look at some engineering uses of these techniques as well. Try and put the differentiation into context. All right. So, product rule. Find the differential coefficient of 3x squared times sine 2x. Get that one out of the way for a minute. So we've got y is equal to 3x squared, one function, times another function, sine 2x. What you can't do is differentiate that and multiply the results together like you did with addition or subtraction. Got to use this product rule formula. Okay, so what we have to do is say let u equals 3x squared, let v equals sine 2x. So we assign the variables u and v to the two functions. And the selection of u and v is arbitrary, but they are the common ones used in maths books and texts. We then have to, if we look at the formula says the differential of that function u times v is u, one function, times the differential of the other function, plus v, the other function, times the differential of the first. So we've got to differentiate both of these. du by dx is equal to, and we've got to find dv by dx on that side. So we've just now been doing them. So what is the differential of 3x squared? Mike, what do we do with this one? Yeah, 2 times 3 is 6. 6x. Yeah. And here, two comes out, cos, look at your table if you're unsure. Yeah, that's the sign that changes, from cos to sine changes to minus, so it is cos, and that 2 stays there, x. Yeah? What we then do is put those bits in that formula at the top there. So we take u, whatever we set to u, 3x squared. That's worthwhile putting these in brackets to start with. Multiply it by dv by dx, 2 cos 2x, and add to that v sine 2x multiplied by du by dx, which is 6x. Here we got 3x squared times 2, 6x squared, cos 2x plus 6x sine 2x. And that can't be simplified any further, can it? Or can it? Yeah, you can. 6x. Tell me what to put in the bracket saying. Okay? So that's that one. Have a go at the other one on the page, the problem 12 one. Okay? They are in the book, but try and avoid the temptation of going into Bird and getting the answer. Have a go at it and see if you can get that one right. Right, what do we reckon? What have we done here then? How have we tackled this one? What do we do first, Jordan? Yeah, so tell me what I should write then.
Well, I changed the B to Y to make it easier to think easier than B.
Okay, yeah, because you got V is equal to, yeah? But V is not a variable in T is your thing. Yeah, I understand what you've done though. So what you done, let Y equals 5T, and let, what's the other half? What other variable you used? You've got to have a, instead of it, you've got rid of, oh, you want Y over this side, do you?
No, I made it so that first equation,
Yeah.
B, I made that Y, so Y equals 5T, not to side 2.
Oh, okay, yeah.
Still easier as B.
Okay then, so you went let U equal 5T.
And B equals 2T.
Yep. They're only temporary variables anyway, just to get you through the process. Next step, Sophie. Differentiate. So differential of 5T is 5. Differential of sine 2T is 2 cos 2T. Yeah? And then we simply plug those bits into that formula. So we want U, 5T, times dv by dx, 2 cos 2t, plus v sine 2t, times du by dt, constant 5. And that simply multiplies out to 5, actually 10, 10t cos 2t plus 5 sine 2t. Can we do anything with that? We could factorise, can't we? 5 times 2 cos 2t plus sine 2t. Yep. And then this question actually says, does it not, determine the rate of change of voltage, which is going to be dV by dt, isn't it? The rate of change, the slope of that function. So that's why you need to differentiate it, because then you're going to find the rate of change, or slope. Am I missing the T? Where's that? Yes, well spotted. Deliberate mistake yet again. Okay, so what that other part of that question is saying is find the value of that function, dV by dt, the rate of change of voltage, when time is equal to 0.2 seconds. So we just substitute p is equal to 0.2 into that equation. So that's 5 brackets 2 times 0.2. This board is starting to get on my nerves already. Cos 2 times 0.2 plus the sine of 2 times 0.2. So we just plug in 0.2 where all those t's are, and you should get an answer. So plug that in your calculator. And so for the quotient rule, we would here, for this example, say let u equal 4 sine 5x, and over this side let v equal 5x to the 4. And then we differentiate this one. How do we do that, guys? Differentiate 4 sine 5x. du by dx is equal to, Dan? How do we do that one? We got a plus 5 and a plus 4. 4 5s are 20. Cos 5x. And the v1, Dan, dv by dx, 5x to the 4. 20x to the 3. Yeah, well done. Okay, and then we just take that detail and plug it into the formula, so we can go dy by dx is equal to, and we got a denominator that is v, 5x to the 4 times du by dx, 20 cos 5x minus u 4 sine 5x times dv by dx, 20 x cubed. And all that is divided by v squared. And then we can simplify a little bit at least. dy by dx. We've got a 20 there and a 5. 25s are 100 x to the 4 cos 5x minus, we've got a 20 and a 4, so that's 80 sine 5x and we want to put our x cubed in here, won't we? 80x cubed sine 5x. Can we simplify 5x to the 4 all squared? No. 5x to the 8, yeah. Laws of indices say raised to a power or raised to another power, we multiply the indices, 5x to the 8. Happy, everyone? What haven't we done? You tell me what's gone wrong there. Something wrong with it. The numerator here is correct. Hence squared to 5. So that should be 25x to the 8. Yeah. Is there anything we can do now? Take out the factor of 20x cubed. Could do. What we've got to put in the brackets? 5x minus 4 sine 5x all over 25x to the 8. Yeah? Okay. So that is quotient rule. And there's a couple of quotient rule questions for you to have a go at. Lastly, there is what's called the chain rule, or function of a function rule. So we've got here a cosine function, and then within the brackets of the cosine function, we've got a linear function. So we've got a function of a function. So in this case, what do we need to do? We say let u equal 5x squared plus 2. Then what we can do is say that y is equal to 3 cos u. So we got rid of one of the functions and assigned to it an arbitrary variable u. du by dx, so we differentiate what we've set to u. So differentiate 5x squared, 10x, and the 2 disappears. Differentiate y equals 3 cos u. That's dy by du, that is, equals minus 3 sine u. Yeah? And then we just plug the numbers in the formula that's up there. dy by dx is equal to dy by du minus 3 sine u times du by dx, 10x. Yeah? So we got minus 3 times 10x is minus 30x sine of u. And then what we do is we replace with the function we set to equal u. So we just plug that u function back in again, and we say dy by dx is equal to minus 30x sine brackets 5x squared plus 2. Function and function rule. Usually dealt with last in textbooks, but actually it's a little bit less tricky than the other two. There's less room for mistakes in that one. Okay, with these, I would say, because I do get to look at maths papers, although I haven't been teaching it, biggest mistakes is making a mistake with negative numbers, dropping a sign off, or not doing the negative number arithmetic properly. Okay, so have a go at the ones that I've set in those three. Yeah, and if you find any of those particularly difficult, if you could let us know during the week, and then I can be prepared to go through one or two of them that you found difficult at the start of next week's session. If you let me know, then I know how much time I've got. This is the issue. We can't spend too long on this recap because we need to go on and do stuff. All right? So that ends first session.